Now let's do another type of hypothesis test called the t-test. And specifically, we're going to start with the one sample t-test. And t-tests are very similar to z-tests. They almost kind of sound the same when you say them. They also test if a difference is due to chance, just like the z-test. The only difference is there's slightly different conditions when we do the t-test. So it says we want to use the t-test and then correspondingly the t-distribution if and only if 3 of these conditions are met. All 3 of these conditions are met. So the first one is that the sample is small. And this is what constitutes as small.
Yeah, that's exactly what I was going to ask.
Yeah, it's kind of different. Wait, have you heard of, what do computer scientists say is a small sample?
I mean, if we're talking about simulation, we think of small simulations like 10,000 samples.
Oh my gosh.
Because we can generate as many simulations as we want. But I'm assuming when you're doing social science, when it costs a lot of money to survey someone or do an experiment, small is probably a very different number.
Yeah, I've heard 25, I've heard 30. I've heard 50, sample size is smaller than those are considered small. Let's just be kind of conservative and say if n is less than 25. That's the first condition for the t-test. The sample has to be small. The second one is that the histogram of the population is close to the normal curve. So the t-distribution is actually bell-shaped just like the normal distribution. And we're going to see how exactly it's different, but we do want the underlying population to be close to normal. And then the last and final condition is that the standard deviation of the population is unknown. And this is usually the case. So the idea is that when the sample size is small, whenever we have small samples, it causes problems. It's not ideal. So when the sample size is small, using the sample standard deviation to estimate the SD of the population is actually not very accurate. So you'll notice that whenever we were doing the z-test or doing inference, I had been saying the standard deviation of the population isn't known, but it's okay. We took a random sample. I can use it as an estimate. I can use the sample standard deviation as an estimate. But when the sample size is small, this presents a problem. So we have to make these adjustments. And it's likely to be too low, actually. The sample standard deviation is usually too low if we have a small sample. So we're going to use something called the SD plus instead, which takes our sample standard deviation and makes it a little bit bigger. And then instead of using the normal curve, we're actually going to use the t-distribution and the t-curves. So here's how the t-curves compare to the normal curve. You can see that the normal curve is actually the dotted line here. And then the t-curves change depending on the sample size. So the smaller the sample, the fatter the tails of the t-distribution, and the shorter the little hump. And then the bigger the sample, the closer the t-distribution gets to the normal curve. And actually, I think here, it says 30 is basically the normal curve. So 25 should be a good estimate. Ideally 30 or higher for the small sample.
And then that says DF. Is that the sample size or what is DF?
Oh, great question, Wade. So this does say DF and it doesn't mean data frame like we have been talking about throughout this series. DF is actually something called degrees of freedom. And this is a statistical concept that will come up definitely in more advanced statistical techniques, but it does come up in the t-test. And basically for the t-test, the degrees of freedom is just the sample size minus 1. So I said earlier that the t-curves change depending on the sample size, and the t-distribution is actually defined by looking at n minus 1 instead of just n. So that is going to come up when we calculate our p-value, because now we don't just have one curve to look at, we actually have different curves depending on the sample size.
So DF is just sample size minus 1.
Exactly. So the only other thing before we can dive into a t-test example that we need to know is how to compute this SD plus, because we do have to use that in order to do the t-test. And if you look here, it is just our sample standard deviation times this constant, which is just the square root of n over n minus 1. So again, we're taking the sample standard deviation and making it slightly bigger by multiplying it by this factor. So it says to note that the SD plus is always greater than the SD. It's easy to remember because it has a plus. But the difference does become negligible as n gets large. So if n is 100, the SD and the SD plus are going to be very, very close to each other. And like I said, there's a t table, just like we have a normal table, but Wade absolutely despises tables. So we're probably going to be able to do this in Python, right?
Yeah, so just like we've imported the normal distribution, the binomial distribution, we can, from scipy.stats, import t.
Amazing. So we can do from scipy.stats. Ooh, that's an easy one to remember. Import t.
And that gives us a t distribution.
Perfect. And so, like I said, there is a different curve for each number of degrees of freedom, where the degrees of freedom is just n minus 1. And the curves are fatter in the tails than the normal curve until we get up to those higher sample sizes. So this actually means that you need stronger evidence to reject the null with the t-test than the z-test. And that kind of makes sense because with these small samples, we have a lot of uncertainty, so there's more likely to be greater error. And let's do our example. So it says, suppose the Keurig coffee maker claims to brew an 8-ounce cup of coffee in 60 seconds, but I think it actually takes more time than that. So to test the coffee maker's claim, I randomly sampled 16 new coffee makers and found the average brewing time to be 64 seconds with an SD of 2 seconds. These must be some old coffee makers. And we want to assume that the brewing time is approximately normally distributed. Great. So it says we want to test whether this difference is due to chance. First of all, what test should we use? And then go ahead and perform it. So now that we know the t and the z test, we need to decide which one to use. And there's only one sample, so there's these 16, that's my n new coffee makers, and we have sample statistics for just one average and one SD. So I know I'm gonna use either the one sample Z or the one sample T test. So let's check if the 3 conditions are met, because we only use the T test if we have all 3 conditions. So the first condition is that we have a small sample, which we do, right? We have n equals 16. So the problem with small samples is that when we use the SD of the sample to estimate the SD of the population, it's likely to be too small. So the second condition is that the data follows the normal curve, and it does, normal data. And then with the sample being small, we need to make sure that we do need to use the sample SD as an estimate. So the last condition is that we have an unknown population standard deviation. And just looking at this puzzle, I do see this SD of 2 seconds here. So does that mean my third condition isn't met?
I don't know.
So let's see, it says, I randomly sampled 16 new coffee makers. So we need to decide,
small, yeah.
Is this the SD for the 16 new coffee makers, or is this the SD for all coffee makers?
That's only going to be the new ones.
Right, yeah, it says that I sampled 16 new coffee makers and got this average in this SD. So this is the SD, this is the sample SD. But there was no information about the population SD, so I can assume it's unknown. So because all of these are met, I am going to do a t-test. And the nice thing about the t-test is that the steps are exactly the same as the z-test. So my first step is to go ahead and state the null and alternative hypothesis. I'm going to write the null in symbols for now. So this, I'm going to say that the true mean is 60 as claimed, right? They say Keurig claims to brew the coffee in 60 seconds. And then the alternative is what I'm trying to test, that I think the true mean is actually greater than 60. So we're going to see which of these is there more evidence for. The second step is to go ahead and calculate our test statistic, which has been Z so far, but we're doing a t-test, so I'm actually going to call it T. Nice thing again, though, is it has the same exact formula as a z-score. It is just the value minus the expected value divided by the standard error. The only difference between the t statistic and the z statistic is that when I'm calculating the standard error, I want to make sure to use that SD plus. as an estimate for the sample standard deviation. 2 is likely to be too small. It came from a small sample, so let's make it a little bigger. So as we're doing this, my value that I got was 64. I expected to get 60 seconds based on the null, right? The null is dull. It assumes that Keurig is doing what they claim. And then let's go ahead and calculate this standard error using the SD plus. So I have to calculate the SD plus first. We're going to do the square root of n over n minus 1 times the SD of the sample. So n in this case is, what was it, 16?
16, yep.
So we can do square root of 16 over 15 times 2.
Square root of 16 over 15 is 1.03, and that whole thing times 2.
Yep, exactly.
So 2 times this is 2.066.
2.066. So we can see this SD plus is slightly bigger than our SD of 2. I know it is only slightly bigger. You probably think, is this even going to make a difference? And trust me, it does make a difference. So now when I calculate my standard error for the average, since I'm dealing with averages here, I am going to use the SD plus as an estimate of the population standard deviation instead of the SD. So I have 2.066 divided by the square root of n, which is 16. And wait, if you could give me my standard error for the average.
Using Python as a calculator, standard error for the average is 0.5165.
0.5165, and now I am going to plug that in.
And what's on your numerator?
So I have, for my test statistic t, I have 64 minus 60, or 4, divided by 0.5165.
So your t statistics is 7.74.
Wow, another, this seems big.
Is that, so is t values and z values somewhat similar in the sense
They're
that
somewhat
7's big?
similar, yeah. So this one is definitely considered big. But let's just see exactly how big. What's the probability I would get my difference between 60 and 64 seconds just by chance, given that the true mean is actually 60? So we are going to find the p-value. And I could draw a t-curve here. The p-value is still going to be my tail, but I'm probably not that great at drawing. I don't know what the t-curve looks like exactly for a sample size of 16. Instead, I'm just going to go ahead and use Python. So this is a positive z-score, so this would be the right-hand tail. Here, I'll attempt it. Something like this.
Looks great.
And then 7 is going to be all the way out here. There's 7. Here's 7.74. And then this is the area that we want. So Wade, how would I find that in Python?
So if you just do 1 minus t.cdf of 7.74, Python's going to give you an error.
Oh.
Because the t distribution is not just one distribution. So it says it's missing one required positional argument, df.
So we need to give Python the degrees of freedom. We need Python to know what sample size we're working with. So wait, I'm guessing I have to do 1 minus t.cdf of 7.74, comma, df or something like that?
Let's try it. df is 15 here.
Yes.
That is exactly right. So comma
df.
df is equal to 15.
And I knew the degrees of freedom was 15. Again, that's just the sample size minus 1. So n minus 1 or 16 minus 1 is 15. And what does that give me for my p-value?
So 6.45 e minus 7.
Ooh, okay, 6.45 e minus 7. 6.45 e to the minus 7. So I'm going to say that's about 0 as well.
Yeah, so this number, this e to minus 7 means times 10 to the negative 7th power. So we have to move everything, move the decimal over to the left 7 places, which introduces 6 zeros before our first 6.
Exactly. So this means the probability of getting our difference just by chance, given that our null hypothesis is true, is so small, it's close to 0%. So that is evidence against the null hypothesis. So in step 4, I'm going to use the same cutoff. My p-value is definitely less than 5%. So we reject the null and conclude there's evidence of the alternative. So if I look back at my null, the null says that the true mean of all Keurig coffee makers is 60 seconds. We're saying the probability of that being the case is low. There's evidence against it. So there's evidence that the true mean is actually greater than 60. So if this was, if we were doing this, we could present it to Keurig and say, you might be lying. But that is the t-test, and hopefully you can see the similarities between the t-test and the z-test. And there are a bunch more hypothesis tests that we can do, but the nice thing is they all kind of follow the same pattern.